Okay, let's do the pre-calculus unit 4 sample test. So given the table of data where X is the month, so 0 month, after 1 month, after 2 months, the Y is the number of cases. And this is in the time of COVID, so when I wrote this, I probably was thinking COVID cases, and we were talking about that in class. So didn't do it much this time, but that's the idea. Now, I didn't specify what the percent is. Now, there's two ways to calculate this. We can talk about what this month's percent is of that, and we could get that by doing 18 divided by 15 and then multiply by 100, so it's 120%, and 120% of 15 is 18. Or we could talk about the increase. This went from 15 to 18, so it increased by 3 divided by where we started from, 15, and we get 20.2, which means 20% increase. So this is in terms of increase, and this is 120% of that, or that means it's 100% plus a 20% increase. You get the idea there? And so if I go to this one, I can do the percentage. That would be 22 divided by 18, which is 122% increase, or 122%. This is 122% of 18, or it's a 22% increase. And you could see that if you wanted to do just that by doing 18 to 22 is 4 more divided by where we started from, 18 in that second month. And you can see it's a 22.222% increase. Now, the question says, what's the average percentage increase? So you need to look at the increase. Now, if you'd worked out the 120 and 122, you would have looked at just the 20 and the 22, and that averages to be 21% increase. Or you can just look at the 20 plus 22, 21. Or you can go 120 plus 122 divided by 2, you get 121. And 121% of the last one means that there was a 21% increase. At 100% of what it was plus 21% increase. Anyway, 21% is close enough for this one. Now, if we do an exponential model, using this percentage, it would be the starting amount, and you notice I gave month 0, so the starting amount was 1,500 cases in hundreds, so 1,500 cases times 121 on average for the growth factor to the number of months. So that would be X is the month, so the number of the month equals Y, the number of cases. Now, if it says number of cases in hundreds, then I want to leave that off and just say 1,500 cases. Okay, so how many months will it take to double the number of cases? So now I really don't even need to, and I have to put the percentage in decimal. So 121% is 1.21 to the X. That's the model. Sorry, I missed the decimal there. So now if I want to know how long it takes to double, no matter how many the starting is, this would have to be 2, so that 2 times the starting amount doubles it. So what I need to solve is 1.21 to the X, and want to know when that equals 2. Now I could graph this and find the intersection, but we know how to do logs now. Let's go to a common base, like 10. So I could say 10 to the log of 1.21, that's another name for 1.21, and that's to the x equals 1.21 to the x is supposed to equal 2. Well, that's 10 to the 2, 10 to the log 2. 10 to the log 2 is 2. So then, just since they have the same base, the powers must be equal. And when I got a power to a power, you multiply. So I get x times the log of 1.21 equals log 2. And then if I divide both sides by the log of 1.21, I get x to be the number of months, how many months, the number of months, x was the number of months, that it'll take to double the number of cases. So to my calculator, and I go log of 2 divided by log of 1.21, and I get 1.38 months. Oh, nope, I forgot a parenthesis. That didn't sound like right. So let's clear that. Let's do this right. Log of 2, close the parenthesis, divided by log of 1.21, close the parenthesis. Now I'll get it. 3.63 months. So the answer to part C is 3.63 months to double the number of cases. No matter how many I start with, that's how long it takes to double them. Okay, now I did another one of these because this time I have one where this was a growth model because the percentage was over 100 or a 20% increase. This one has a decrease. You can see it's going down. So now we have to do this problem. Similarly, we can take 0.71 divided by 0.75. It's always the later one divided by the previous one. And that gives us 94%, 95% rounded. 94, maybe I should have done 94.7, but I'll just put 95%. Or the change, or the increase, or in this case, decrease, would be the 71 minus 70, 0.71 minus 0.75 is 0.0 minus 0.04 divided by the starting amount, which was 0.75, and we get that it went down by, if I move the decimal 2 places, 5.3%. Down by 5.3%. This is 5.3 as opposed to, I should probably carry this one decimal further, 94.7% rounded off, 94.7. So this one is 94.7% of that one, or it's a loss from here to here of 5.3%. You could get this number by taking 94.7 from 100, and you would get 5.3. All right, let's figure the next one. So I always take the next one minus the previous one, so 0.68 divided by 0.71, and you get, this time we get a 95.8%. This is 95.8% of that number, which means it went down by 4.2%. Because 100 minus 95.8 is 4.2. Or I could say this decreased by 0.03 divided by the previous number, which is 0.71, and it gives me the 4.2%. Negative because it's a decrease. Let's do the next one. 0.64 divided by 0.68, and that's a 94.1%, which means it went down by 5.9%. And the next one, 0.61 divided by 0.64. This is 95.3%. If I take it from 100, that's telling me it went down by 4.7%. So here I asked what's the average percentage decrease, so I want the average of these decreases. Now I can take the average of the other ones and then subtract it from 100, or I can just do the average of these. Either way. Now to do average, I presume you can do that. So we have, these are all negative, so I'm just going to leave the negatives off while I do the average. I got 5.3 plus 4.2 plus 5.9 plus 4.7, and then that's 1, 2, 3, 4, so I got to divide by 4, and the average decrease, which I asked for, the decrease is 5.03% average decrease. Pretty close to 5% decrease. Okay, so an exponential model. Well, we do 1 plus a negative 5.3%, or we can just use the average of these, which would be 94.07%, or in decimal be 0.9. Always do that. I want to do it in decimal, so it's 0.9407 is the base to the number of years, x was in years, and that gives me the number of grams still there. Oh, but I started with 3/4 of a gram, so I got to put that in there. 0.75 for the starting amount, and that will tell me how much there is after some time. There's an exponential model. And I can test it just to make sure that it's working. I can say 0.75 times 0.9407 to the, and let's just see how it works for 3. So I'm going to try 3. I hope I get something close to 0.64. 0.62. Yeah, it's close. And if I put 4 in, it should be close to 6.1. And it's 0.58. It's a little low. Let's try 1. And we get 0.70, which is close. All right. Let's see, 5, 4, 5, 1, 5, 3, 503. Oh, I know it's wrong. 100 minus 5.03 is 9497. There's why I'm getting a little farther off than I wanted to be. I didn't subtract that from that correctly. 100, that's what I get for doing math in my head, minus 5.03 is 9497. Boy, I'm making several mistakes here. Now let's test it. So I should have 0.75 parenthesis 0.9497, close parenthesis, to the 3, and it should be close to 64, and it's really close to 64. That's a much better fit. And if I did it again with 4, it should be close to 61, and it comes out really close to 61. Now I'm getting much better answers. Okay. Now we can move on. What if I did a base E model? Okay. So now we do the amount after some time is the starting amount, 0.75. E to the growth or decay percentage. In this case, we decided it's negative 0.0503 times the amount of time. That's in X, so I probably should put X there and Y here, but I'm going to leave it like that. And this should give me a pretty close model of this. Let's check that. So I'm going to type in 0.75 e to the negative 0.0503 times, let's do it for 3 years. Times after 3 years, and we should get that 64 number. Pretty dang close. And if I put in 4 instead of 3, second entry, change that to a 4, we should get close to the 61. And let's see if we do. Pretty close. Okay? So that's an E model for it, where we put the increase or decrease percentage in. Here we put not the increase or decrease percentage, but the 100 plus or minus the increase or decrease. The original percentage, these divided. So what's the half-life? Well, we could use this one and try to make this be 1/2, or we could use this and make that be a half. Either way, so I'm going to do them both, just so you can see how it works. If I'm going to get half of this left, that makes it a half-life. This has to be 1/2. So 0.5 would equal negative, 0.9497 to the X or T or whatever. Now, I'll go to a common base, say 10, and I'll say 10 to the log of 0.5, another name for 0.5 in base 10, equals 10 to the log of 0.9497 to the X. Now I have a common base, so the powers need to be equal. This is what I have to do. 0.5 is log 10 to the log 0.5. 0.9497 is 10 to the log 0.9497, and that's to the X. Since they have the same bases, the powers must be equal, and we got a power to power, we multiply. So we're going to get log of 0.5 equals X times the log of 0.9497. So I'll divide by this log on both sides. And so X would equal the log of 0.5 divided by the log of 0.9497, which equals log 0.5, close parenthesis, divided by log 0.9497, 13.4 for x, the half-life in years, it's set up there. So 13.4 years. Now, if we do the E, we'll probably get slightly different answer because E is basically compounding continuously, where this is compounding per year. So they're not quite the same, but they'll be close to the same. We would start off with 0.5 equals E, this part would have to be 0.5, e to the negative 0.0503 t. This is in base e, so I'm going to write this in base e, which would be e to the ln 0.5. And so now ln of 0.5 would have to equal negative 0.0503 t or x. And so to solve for the t or x, we're going to divide by that. And so we're going to have, I'll just do it on the calculator. We're going to have ln 0.5 close parenthesis divided by negative 0.0503, and we get the time to double is 13.7 years. Okay? And I would accept either method. You're showing me how to solve. You're showing me that, you know, this thing has to be 0.5 to be the half-life. This one's more correct than that one, but they're both close enough for what we're doing. Okay? Page 2. Number 3. All of these can be written in base 2. So that's 2 to the negative 1 times 2 squared for the 4 to the 3x equals 2 to the x plus 1. So here we'd multiply, so that's 6x, and multiplying we add, so we get 2 to the 6x minus 1. We multiply these and then add that, equals 2 to the x plus 1. They have a single base, they're both the same, so the powers must be equal. 6x minus 1 must equal x plus 1. Subtract x. Add 1 to both sides. And x equals 2/5, which is also 0.4. So either answer is fine. We should always check. So I'm going to check real quickly. 1/2 times 4 to the power of 3 times 2/5. And that's the left side. Now we'll do the right side. 2 to the power of 2/5 plus 1. And exactly the same number, so 0.4 works. Now here, there's not a number like 2 as a common factor of all those. There's no common factor, so we need to go to a different base. I'm not sure whether you like base 10 or base E better, but I'll put 5 is 10 to the log 5 times, that's already in 10, so that's 2 minus x. I don't have to change that base. equals, and this would be 10 to the log 7 to the x. And when we multiply, we add powers, so we get 10 to the log 5 plus 2 minus x equals 10 to the x times the log of 7. So this power has to equal this power. So I got to subtract x from this side, so I'm going to get log 5 plus 2 equals x log 7 plus x, adding x to both sides. I can factor an x out of this, and I get log 7 plus 1 times x, because x times that is the 1 gives you x, and x times this is x log 7, equals log 5 plus 2. So then I would divide both sides by the thing that's times x, and I get x is log of 5 plus 2 divided by log 7 plus 1. And I can't combine these or simplify those anyway, so I'm going to type that in to get a decimal approximation for the answer. And this is a fraction, so I'm going to start off with a fraction here and do log 5, close parenthesis, plus 2. And then in the denominator, I have log 7, close parenthesis, plus 1. And I get x is 1.4677, blah, 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 blah. Now to check it, here's a nice little trick. I can take this number and store it with this stow button here in x. And so it's saving it in an x. In fact, if I type x and press enter, it gives me that number. So now I can type in 5 times 10 to the 2 minus x, and it knows x is that number, so it's going to use that. And it gives me this for the left side. And the other side is 7 to the x, so I'm going to write 7 to the x, and they match. So that is the correct answer, and that's the exact answer, and this is the decimal approximation. Okay, next one. So this says 3 times, to what power do we take 1/5 to get 25? Well, we know 25 is 5 squared, but this is 1/5. To turn 1/5 over, we'd have to use a -2. So 1/5 to the -2 is 25. You can check that on your calculator. And so this whole thing, which asked for the power that makes 1/5 be 25, the answer is -2 for this part, times 3. So the answer to this is 3 times -2, which is -6. And that's exactly right. It's not a decimal approximation. Now this one, when you write e to the ln, that's just another name for whatever this is. So this is just pi over 3. Same would happen if you said 10 to the log base 10 of pi over 3. That would be pi over 3. Now this says, to what power do you take 10 to get 10 to the 15th? Well, you have to take 10 to the 15th power to get that. Or you could say log rule, this goes down, and you could call this 15 times the log of 10. And since this is base 10 understood, to what power do I take 10 to get 10? That would be 1, and 15 times 1 is 15. Couple ways to look at that. So now when we have to solve log equations, we like to get it down to a single log. And so this is where we practice some things in class on putting these into a single log. For instance, this 2 could go up as a power of the x. And when you subtract logs, you divide the arguments, so we get log, and this is understood base 10, because there's no base on any of these, so that's understood 10. And you would divide, because when you subtract powers, it comes from a division problem. And that's supposed to equal 1. Now, some of you say, well, I'm just going to write this another way. That's 1 is to what power do you take 10 to get 10? So this would have to equal 10. Or you could say 10 to the 1 is this. Either case, you get x squared over x minus 2.5 equals 10. 10 to the 1 is 10 equals this. Or 1 is log base 10 of 10. 10 has to equal this because they're both the same log. Okay, now to solve this, I would multiply both sides by x minus 2.5. So they cancel here. And this one times x minus 2.5. And I get x squared equals 10x minus 25. So I have a quadratic. To solve that, we need to have it equal to 0. So I'm going to write x squared minus 10x plus 25 equals 0 by subtracting 10x from both sides and adding 25 to both sides. Now when it's in that form, I can do the quadratic formula where 1 is a, negative 10 is b, c is 25, or I can factor. If it factors, and I believe this one does, x, and let's see, I think if I go minus 5 and minus 5, I'll get this, which means there's really only one possible answer, not guaranteed it's an answer. Looks like it could be 5. You always want to check when you solve log equations. So we got to check and see if 5 actually works. So we're going to do 2 times the log of 5 minus the log of 5 minus 2.5 and see if we get 1. So 2 log base 10 of 5, close parenthesis, minus log, and I'll just write it in so I don't make a mistake doing mental math, close parenthesis, and we get 1. So that worked. And we can move on to page 3. Page 3, another log equation. This time it's adding, and when they're adding, you multiply the inside. There's no power in front, a number in front that we can put up a power, so we're just going to have log base 3 of x plus 4 times x minus 2. And that's supposed to equal 3. So now to write this out as an equation, this says to 3 to the third equals this. So x plus 4 times x minus 2 has to be 3 to the third, which is 27. Well, if I multiply this out, I can't just say the answer is -4 or 2 because it's not equal to 0. So I'm going to have to multiply this out, expand it, x times x minus 2x plus 4x minus 8 equals 27. Get it equal to 0 by subtracting 27 from both sides. Combining these terms, I get x squared plus 2x minus 35 equals 0. And if that's the case, now it's equal to 0. So if I can factor this, I could use the quadratic if I can't factor it or complete the square, but I think I can factor this. This is x and x. 35 is like 7 times 5. And I want to have a plus 2, so I make it plus 7x minus 5x. And this does make -35. So this says x has got to be either a -7, maybe, or x has got to be plus 5. We got to check these. Now, it should probably work with both of them unless the argument becomes negative. If I put -7 there and add 4, I get -3. You can't do logs of negatives. So -7 has to drop out. I can't even get to there. That would have been -9 though, and so it wouldn't have worked there. Now, if I put 5 in, I get 5 plus 4 is 9. And the power I take 3 to get 9 is 2. And if I put 5 in there, I get 3. And the power I take 3 to get 3 is 1. So 2 plus 1 does equal 3. So this checks. So I have one answer, even though it looked like I might get 2. Okay, we have a radioactive isotope. And we're going to do the normal radioactive equation. And it says determine K if 10 grams, so that must be the starting amount, decays to 2 grams in 12 years. So the amount after 12 years, which was 2 grams, the amount at the end is equal to the starting amount, which was 10 grams, and it's E to some constant for this radioactive isotope times the number of years, and that was 12. So we need to solve for the K. So I'm going to divide the 10 out right away, and that makes 2 divided by 10 is 0.2 equals E to the 12K. I need to write this in base E, so this would be E to the ln 0.2. So ln of 0.2 equals 12K. And if I divide by 12, I get the constant that's characteristic of this particular isotope. And it will be the one that is for all cases of it. So it'll give me the equation. So ln of 0.2, close parenthesis, divided by 12 is, so the constant that I asked you to find is negative 0.1341. So now my model is starting amount E to the negative 0.1341 times T. So it says if you started with 50 grams, so I got a new starting amount. It doesn't affect the K, it's still the same K. And I want to know how much is still active after 20 years. So the amount active after 20 years is the amount we started with, and I said 50 grams, times e to the characteristic K for this isotope, negative 0.1341, which means it loses 13% of its amount pretty much each year, times the number of years, which was 20. So we're going to figure out the amount left after 20 years. And it comes out to be 50 times e to the negative 1341 times 20. I got to get it all in the powers. If you're doing a calculator that doesn't put up as a powers, you got to put those two in parentheses. Enter, and we get 3.42 grams would be left. 50 would go down to 3.42 grams. If you started with 50 grams, how much is still radioactive? 3.42 grams. Okay. In how many years will it be down to 10%? So to go from any amount down to 10%, this would have to be 10% in decimal. 0.1, that's 10%, would have to equal e to its characteristic number, negative 0.1341, the constant for this isotope, times T number of years. Well, we might as well write this as e to the ln 0.1, that's another name for 0.1. So we see that ln of 0.1 has to equal negative 0.1341 t. I would divide by this coefficient. And get t to be ln 0.1, close parenthesis, divided by negative 0.1341. 17 years, it'll be down to 10% still left. I think t was in years, so let's make sure. Yes, it's in years, so t equals 17.17 years to get to 1% left. Half-life, that'd be when does it get to be 50%? So everything would be the same except instead of 0.1, this would be 0.5. So it's going to be ln of 0.5 divided by negative 0.1341 is the t for the half-life. So ln 0.5, close parenthesis, divided by that negative 0.1341, and we get the half-life to be 5.17 years. Okay, last page. Suppose you invested $3,200, so that's the starting amount, at an interest rate of 6%. How much would be there in the account after 10 years if you had a compounded quarterly? So we're doing our compounded formula. The amount after some time is the starting amount times 100% plus 6%, of course in decimal, divided by how many times we're compounding in a year. And that was n, which would be 4 for 4 times a year, quarterly, to the nt, so 4 times the number of years. And I said 10 years. So, and the starting amount was the 3,200. So all I have to do is type that in. 3,200 parenthesis 1 plus 0.06 divided by 4 to the 4 times 10 or 40. And so the 3,200 has grown to an amount of $5,804.86. How long would it take for the balance to grow to 4,000? So now we're going to put 4,000 in for the amount after some time. 3,200, 1 plus 0.06 divided by, we're still compounding quarterly, to the 4t. So we want to know how long it takes. So we're solving for the t. So the first thing you want to do is divide the 3,200 out of there. So we get 4,000 divided by 3,200. So we're at 125% of what it was. This is 125% of that. So it's 1.25, which we're going to write in maybe base 10. So we're going to take 10 to the ln, or L log of 1.25 has to equal, well, this number. What is that number? 1 plus 0.06 divided by 4 is 1.015. So we're going to write it as 10 to the, I'll write it up here, 1.015 to the 4t. If I wrote this in base 10, it'd be 10 to the log of 1.015, and that would be to the 4t. So now they're both in base 10. So this exponent has to equal this exponent, and here we'd multiply it, so it'd be 4t log of 1.015. So I'm going to divide both sides by 4 times log of 1.015. And I get the t for the amount of time to get to 4,000 is going to be log of 1.25 divided by, we've got two things here, so I'm going to put parenthesis, 4 log 1.015. Close parenthesis, and we get 3.75 years. For 3,200 to grow to 4,000. How long would it take to double? Well, then instead of trying to make it 1.25, we're just trying to make it be 2. This part be 2. So all of this would be the same, except we'd have a 2 there. So I'm going to have log of 2 divided by 4 log of 1.015 will be the time to take it to double. So I can just get my last equation and just change the 1.25 to 2. And we get 11.64 years. And D, how much would be in the account in 10 years if it was compounded continuously? Okay, compounded continuously would be the amount after some time would be, of course, the starting amount, e to the interest rate times t. So it would be the amount after 10 years, compounded continuously, would be the starting amount, e to the APR, which was 6%, in decimal, that's 0.06, times the number of years, which we decided is 10 years. So we're just going to do that on the calculator. 3,200 e to the power of 0.06 times 10. And we get $5,830.78. So we figured out how much was in the account after 10 years up here, 5,804, compounding quarterly, and we get a little bit more if we compound continuously. Looks like about $26 more. And that's the test.